Hello, this is Gary LaRue, Technical Editor at Microwave Journal. I'd like to welcome you to today's webinar discussing design innovations in 5G mmWave front-end modules and phased arrays, presented by Baljeet Chandhok of GlobalFoundries. Before we begin the presentation, let me cover a few items about the ON24 webinar platform. In the center of your screen, you'll see a window containing the presentation. You may enlarge this to full screen to have a better view of the slides. The window labeled Resource List, which you can access from the green box at the bottom of your screen, contains a copy of the presentation, which you may download at any time. The webinar is being recorded and will be available for replay within about an hour after we finish, allowing you to watch it again and recommend it to any colleagues who weren't able to join this live event. You'll find a link to the recording in the Events section of the Microwave Journal website. After the presentation, we will have time for Baljeet to answer your questions, so if you'd like to ask one, just type it in the Q&A box on your screen. If you have any technical problems, please click on the yellow box with the question mark at the bottom of your screen, which will take you to a user's guide. You can also submit a question in the Q&A box, and we'll try to assist you. And that's it for the instructions. Now let me introduce Baljeet. Baljeet Chandhok manages the GlobalFoundries portfolio of RF solutions. He's responsible for defining new product technology, product marketing, and working with customers to ensure they meet their design challenges. Prior to joining GlobalFoundries, Baljeet worked in leadership positions at IDT, ON Semiconductor, and Cypress Semiconductor. He has an MBA from Arizona State University, a master's in telecommunications from the University of Colorado Boulder, and a bachelor's in electronics and telecommunications engineering from the University of Mumbai. Baljeet, I'll turn the screen over to you now, and I'm looking forward to your presentation.
Thank you, Gary, for the introduction. Hello, everyone. Thank you for joining the webinar today. The agenda for today's webinar, I will go over 5G mmWave applications, how 5G NR standards are driving increasing radio complexity and cost, and what are the technology requirements for mmWave applications. Then I'll talk about phased arrays and front-end modules, give a brief overview of different types of beamforming architectures for phased array antenna systems, followed by impact of semiconductor technology on the number of phased array elements. Then I will talk about technology to meet the requirements of 5G mmWave applications and end the webinar with a summary and a Q&A session. 5G is not just a new generation, but a new kind of network. 5G needs scalability and adaptability across extreme variations and use cases, as you can see on the slide. For IoT applications, which need to connect to a massive number of things, ultra-low cost and ultra-low energy consumption is a requirement. For ultra-mobile broadband applications, extreme broadband is needed due to applications such as 4K video, gaming, and ultra-high capacities to support the data rates needed for these applications is a requirement. For ultra-reliable mission-critical applications, such as services to remotely controlled vehicles, medical procedures with ultra-reliable links, use cases like autonomous vehicles, remote medicine, ultra-low latency, and ultra-high reliability is a requirement. Proximal and aware services to empower and optimize new user experiences need deep awareness. As you can see, all these requirements for 5G drive diverse use cases and applications. Now, let's look at some of the mmWave applications. What you will see is, for all these applications, they use phased array antenna systems. Instead of a single antenna, phased array antenna system uses multiple elements or array of antennas to do constructive interference for receiving and transmitting the signal by focusing the energy from the beam in a particular direction. Millimeter wave applications include ADAS or advanced driver assistance systems, auto radar for automotive collision detection. It includes millimeter wave backhaul, fixed wireless where millimeter wave phased arrays are used, 5G handset and infrastructure devices like small cells, femtocells, picocells, microcells, all use phased array systems for beamforming. WiGig, Wireless Gigabit Alliance, which provides multi-gigabit per second speed wireless communication technology operating over the unlicensed 60 GHz frequency band, also uses millimeter wave beamforming. Satellite communication, as you know, uses beamforming today for geosynchronous satellite communication for mobile airborne applications. This is when you're in the aeroplane, you're able to communicate and have broadband internet that is using phased arrays, using satellite communication. In addition, phased arrays are also being used in low Earth orbit satellite communication for broadband communication to focus the beam to the satellite and vice versa. Some of the key benefits of using phased array for these applications are to focus the beam, which allows spatial multiplexing, where the beam that is being broadcasted is a very narrow beam and is targeted to a single user. As we go to millimeter wave, the antenna dimension shrinks. We can put a lot of antenna elements in the phased arrays, which allows for spatial multiplexing. The power levels transmitted by each antenna element is reduced dramatically. This happens because concentrating all the energy in one direction instead of broadcasting in a big beam with a wide angle. Since the transmit power requirement is reduced, the requirement for each power amplifier connected to each phased array element is reduced. This allows silicon-based technologies to be used for phased array antennas instead of the 3-5 semiconductors like gallium nitride, gallium arsenide, which are typically used for high output power amplifiers. Some of the common system blocks for millimeter wave applications are phased array antennas, millimeter wave up and down converters, millimeter wave local oscillator generation, front-end module, which is composed of millimeter wave LNA and power amplifiers, switches, phase shifters, power combiners, and all these typically operate between 24 to 100 gigahertz, as you can see on the slide. Now I'm going to go in detail into some of these applications. Let's start with satellite-based internet and mobile communication. Satellite-based internet and mobile communication provides connectivity to the population in remote regions which does not have broadband connectivity. Geosynchronous satellites are already providing connectivity in flights, airborne vehicles, and in different parts of the world. LEO or low Earth orbit satellite service will be launched in 2019 with companies like OneWeb and SpaceX planning to launch services. For LEO satellites, the distance from the Earth is less than 2,000 kilometers, whereas for the geosynchronous satellites, it is 35,800 kilometers. Hence, LEO satellite communication has very short lifetime. As you see on the slide, you have direct satellite to home broadband connectivity using phased array satellite ground terminal. Now, I'm going to talk about fixed wireless. Fixed wireless is an alternative to fiber-based broadband. It is the first use case of commercial millimeter wave broadband. Fixed wireless provides high-speed internet service via an outdoor antenna or an indoor Wi-Fi gateway router. As you can see in the figure, there are access points which provide fixed wireless connectivity at 28 gigahertz and 39 gigahertz. The access points talk to the outdoor antenna, which would be the customer premise equipment, and then you get internet connectivity. Fixed wireless will be the first millimeter wave broadband application, and it can be leveraged then for 5G mobility later on. Now let's talk about small cells, macro cells. Small cells also use phased arrays. As you can see, for a small cell, are small base stations which have a range of few meters to 2 kilometers in radius. There are three types of small cells called femtocells, picocells, microcells. They are considered small compared to the macro cell or the macro base station, which can have a range of greater than 30 kilometers. Now let's look at each of these cells. Femtocells are typically for a very small area, such as a home office or a dead zone within a building. They are designed to support very few users, anywhere from 1 to 30 users, and have an output power of up to 0.25 watts. Picocells have greater capacities and coverage areas, supporting up to 100 users with a range of up to 200 meters. Picocells are frequently deployed indoors to improve poor wireless and cellular coverage within the building, such as an office floor or a retail space. They have an output power of 1 watt. Microcells can cover areas up to 2 kilometers in radius and can be deployed to temporarily in anticipation of high traffic, such as in stadiums, sporting events, on a game day, but they're also installed as a permanent feature of mobile cellular networks. They can have an output power of 10 watts. Output power is the key, and it dictates the technology selection for each of these small cells, picocells, femtocells. In a heterogeneous network, small cells will work in conjunction with the macro cells to provide uninterrupted coverage for end users. Traffic density and end coverage will lead to small cell deployment driven by sub-6 gigahertz 4G, 5G, and ultimately millimeter wave using phased arrays with better coverage at the edge of the network via spatial multiplexing. Now let's talk about how the front-end modules are evolving. This slide shows the transition as we move from 4G to 5G. In 4G, we are looking at sub-6 gigahertz operation, while in 5G, we are looking at greater than 25 gigahertz. In 4G, we have a small number of antennas, while in 5G, we are going to phased arrays. We'll be talking in detail about this in the later part of the presentation. In 4G, we transmit in all directions, which require very high output power from a single power amplifier. As we move to 5G and phased arrays, we have many lower power amplifiers that aggregate into a beam of energy in a specific direction. Hence, you can see pencil beams from phased array antennas as shown on the slide. 5G is changing the front-end module architecture, driving the integration of the power amplifier, the low noise amplifier, the switch and phase shifters for beamformers. The use of high frequency bands for millimeter wave is emerging as a key 5G technology. The use of this band is very compelling because large amounts of bandwidth in hundreds of megahertz are available at these high frequencies, which enable extremely high data rates and significant increase in capacity. So as you know, the sub 6 gigahertz spectrum is very congested. So millimeter wave 5G enables you to have hundreds of megahertz of bandwidth available for high data rates. So that's a huge benefit. However, there are some drawbacks in which there's not enough robustness for mobile broadband applications due to increased propagation loss at millimeter wave frequencies and susceptibility to blockages. So it's like building penetration. All of those are some of the issues that millimeter wave 5G faces. However, advanced antenna techniques that are being introduced with 5G new radio or 5G NR, the global standard for 5G, are changing this. So what you will see is 5G will be rolled out in stages and will leverage the existing 4G LTE backbone for 5G communication services. Several enhancements to 4G LTE systems such as license assistant access and LTE over Wi-Fi will be employed to make the transition. An initial rollout of sub 6 gigahertz bands will be deployed and will use techniques such as massive MIMO, which you see on the screen, to provide individual users and groups of users high data rate services. A second rollout, expanding network capacity and driving even higher data rates, will be deployed by leveraging millimeter wave bands where there is little or no interference or congestion. Both of these rollouts, what this means is they will enable a more complex radio, which will need to not only work with the new network protocols, but also support the legacy protocols and bands as well. So as you can see, 5G NR standards are driving higher data rates and improved mobile user experience, resulting in greater complexity in radio and higher costs as well. Now let's talk. So far we have covered the different applications. Now let's talk about some key technological requirements for these different applications. In SATCOM, we are receiving the signal from far away. So the key figure of merit is the noise figure. For RF front end, the key technology requirements are low LNA noise figure and low VCO phase noise. For digital front end, low logic power performance area and low power ADC DACs are a requirement. It needs to be cost effective for adoption in different parts of the world. For millimeter wave small cell fixed wireless, the challenge is on the transmit side, with the power amplifier output power and the power added efficiency determining the array size and cost. Minimizing routing loss to the antenna in larger arrays is critical. For millimeter wave mobile 5G, again, power amplifier PAE determines the battery life. Battery life is the key figure of merit for millimeter wave 5G handsets. Okay, so let me summarize what we have learned so far. We have gone over 5G millimeter wave applications, how 5G NR standards are driving increasing radio complexity and cost, and what are the key technological requirements of millimeter wave applications. In this section, I will talk about how phased arrays and front-end modules address millimeter wave application requirements, give a brief overview of different types of beamforming architectures for phased array antenna systems, followed by the impact of semiconductor technology on the number of phased array elements, and how phased arrays address these different applications. So let's talk about how the phased arrays work. Instead of a single antenna, phased array antenna systems use multiple elements, as you can see on the slide, or an array of antennas, and do constructive interference for receiving and transmitting the signal by focusing the energy from the beam in a particular direction. On the transmit side, each element of the array generates power. In addition, the array has array gain. So the equivalent isotropic radiated power, or ERP, is the product of the transmit power and the antenna gain in a given direction relative to an isotropic antenna of a radio transmitter. So keep that in mind. The ERP increases by a factor of n square, or 20 log n. And the reason for that is each element is adding power and the array adds array gain and you get n square factor. As a result, for the same ERP, or effective isotropic radiated power, the power per phased array element is lower. As we go to millimeter wave, the antenna dimension shrinks. So, and the power levels transmitted by each antenna element reduce drastically. This happens because we are concentrating all the power or energy in one direction instead of the wide beam that you have in a typical antenna. As the transmit power requirement is reduced, the requirement of each power amplifier connected to each phased array element is reduced. This allows the silicon-based technologies to be used for phased array antennas instead of C5 semiconductors like gallium nitride, gallium arsenide, which are used for high power amplifiers. So this is the key point out here is because of this less number of transmit power per antenna element and phased array elements or antennas, you are able to use silicon technologies. Now, phased arrays have multiple antenna elements, so they are also called active electronically scanned array to do beamforming or beam steering. Now, the other concept out here is beam steering or beamforming. So let's talk about what is beamforming. The wavefront, so as you can see, right, in the phased array system, you have multiple elements, and then you have narrow beams, which is focused to users. Now, the wavefront of an RF signal that will arrive at each antenna element at different times with different phase due to the different path lengths traveled. So you need phase shifters to compensate for this electrical path difference by adding a variable phase to each path so that signals from a desired beam direction add constructively while signals from other directions cancel. So this is known as beamforming. Now let's talk about the different types of beamforming. There are three different types of beamforming architectures. There's analog beamforming, there is digital beamforming, and there is hybrid beamforming. For any phased array system, the ideal separation between the elements of the phased array is lambda by 2 or wavelength by 2. So what that means is for a 30 gigahertz RF signal or wavelength, you are looking at a separation between phased array antenna elements of 5 millimeters. Now, let's start with analog beamforming. So as, what I've shown on the slide is 4-element phased array. The small phased array, but just to explain the concept. And what you see is each of this phased array has the front end, and then it has the digital ADC stacks and the baseband. What you are seeing is in the front end, you have the switch, the low noise amplifier, and phase and amplitude control. At the receiver, at the transmitter, you have the power amplifier, phase amplitude controller, and the switch. Now, these have to be right next to the antenna elements. For analog beamforming, the phase and amplitude adjustment is done for each element at RF frequencies. And then they are combined at the receiver or split up at the transmitter. And then the signal is done up and down conversion, and then it goes to ADC and DAC to the baseband. So for n number of elements, in this example, 4 elements of the phased array, there is only one ADC DAC, one up and down converter, and a single baseband. So this is analog beamforming. So you're doing all the beamforming or changing the phase in analog domain or RF domain. In digital beamforming, you do that in the digital domain. So you have the phased array element followed by the front end, and then for each element of the phased array, you have up and down converter, ADC DACs, digital phase shifter. So you convert it from RF to the baseband, and then you do digital phase shifting, and then you combine it and give the signal to your baseband processor. So what you see is there are a lot of number of components, because in this example you had 4 ADC DACs, whereas for analog beamforming you only had 1 ADC DAC. 4 up and down converters, you had only 1 up and down converter. So digital beamforming has a lot of components. Hence, it has extremely high power consumption as well. The benefit of digital beamforming is, because it's digital, you have digital phase shifting, you can get a very precise, accurate beamforming. On the analog side, since you're doing phase and amplitude control in the RF domain, there is extreme complexity in phase shifting. Of course, I mean, you're doing it at 30 gigahertz, 28 gigahertz. And then the second thing is it's sensitive to interconnect losses. But the benefits you get are lowest power consumption or dissipation. So you don't have all these ADCs and DACs, all these up and down converters. You just have one. And then you have smallest number of components. So this is how you compare analog beamforming architecture versus digital beamforming architecture. Now let's talk about a hybrid approach where you're using both analog and digital. So you have analog beamforming on the front end, and then you have digital beamforming after the ADC DACs. And this hybrid beamforming approach is very useful for large arrays, because for large arrays you can't have, let's say, 256 array. You cannot have 256 ADCs and DACs, right? So you have part of beamforming done on the front end using analog beamforming and the rest. So you get the benefits of both. So that's hybrid beamforming. Now I'm going to talk about the effect of antenna array layout on the beamforming architecture. This is very critical because we are talking in mmWave, so extremely high frequencies, extremely high interconnect losses. So the placement of your front-end module with reference to your phased array elements is extremely critical, and that's what's shown out here in the slide. So what we have shown is you have the phased array elements in orange, and then right next to it we have the analog beamformer front-end module with mmWave up and down converter, such that it gets to the intermediate frequency or baseband. So benefit of this approach is course, you avoid the large interconnect losses that you have at RF frequencies. So now you are at IF frequency or baseband. IF can be sub 6 gigahertz, so significantly less losses as compared to at 30 gigahertz as an example. And then you can have ADCs, stacks, and modems to get to baseband. The distance between the antenna elements of a phased array should be lambda by 2 for ideal beamforming. So for a 30 gigahertz, the distance is 5 millimeters as an example. Now this shows you a 5G mmWave FEM-centric architecture. So you have the antenna subsystem, and then you have the mmWave radio interface, and then you have the IF transceiver, ADC's digital interface, and then finally the baseband processor. So this is an example of digital beamforming. As you can see, you have multiple ADCs and DACs, and multiple RF up and down converter. In analog beamforming, you would only have one ADC and DAC and one up and down converter. So that's one way to differentiate between analog and digital beamforming. In addition, your conversion is all happening in analog domain at RF for phase shifting, and digital, it's all done using digital phase shifting and baseband. The benefit of this approach, this is the IF-centric architecture. So the benefit of this architecture is you have a use of RF-IF interface allowing for flexible placement of phased array antennas. So FEM components and allows more manageable frequency to be routed for baseband processing. Now I'm going to talk about the impact of semiconductor technology. Just a couple of definitions before we get into this. G by T. So antenna gain to noise temperature is the figure of merit in the characterization of antenna performance, where G is the antenna gain in decibels at the receive frequency, and T is the equivalent noise temperature of the receiving system in kelvins. For an active phased array of n elements, for every element added to an array, G by T of a receiver array increases by 10 log n, where n is the number of elements, and the earth or effective isotropic radiated power of a transmit array increases by 20 log n. So the performance of semiconductor technology with reference to the power amplifier, output power, and the low noise amplifier noise figure determine the array size needed to meet the system requirements. And this is what I'm going to show you in this slide by a couple of examples. So looking at on the graph on the left hand side, G by T being the figure of merit, if you want a G by T of 5 and the noise figure of your low noise amplifier in the technology that you're using is 2.5 dB. In that case, you would need 500 radiating elements to achieve the G by T requirement for your system. Now, let's say you use a different technology where you can get a noise figure for your low noise amplifier of 1.5 dB. Then what happens is the number of radiating elements you need to meet your system G by T requirement comes down to 250. A huge reduction in number of elements. That means huge reduction in the size of phased array. That means huge reduction in the cost of your system. Now let's look. So this was on the receive side, where noise figure is the figure of merit. On the transmit side, the figure of merit is the output power of your power amplifier. And how much is your effective isotropic radiated power? So let's take an example. So you want your ERP to be 40 dB WI. So for that, if you can have for each element transmit output power of 20 milliwatts, then you would need roughly 500 radiating elements. However, if you choose your semiconductor technology such that each element power amplifier output power is 50 milliwatts, it comes down. So effectively for 50 milliwatts, it comes down to roughly 300, anywhere between 250 to 300 radiating elements. So the key point out here is the technology with better receiver noise figure and higher transmit power output will lead to fewer array elements for a target receiver antenna G by P and transmit antenna ERP respectively. The technology with better figure of merit relates to smaller array, relates to lower cost and smaller area. So that's kind of the crux of this, is the impact of semiconductor technology is huge for phased array systems. And I'll give you an example of some semiconductor technology and how it will relate back to this as we move on in the presentation. This analysis was done courtesy of mmWave, and they have done a similar webinar as well on this analysis. Now moving on to choice of technology. Is a and I'm going to compare digital and RF. The choice of technology is a careful balance of technology, device, and application metrics. So for digital, you're looking at delivering the fastest speed and the lowest power at the highest density at the lowest cost. So it's all about scaling. So you want to get the lowest power at the highest density at the lowest cost. So that's digital for you. However, for RF, the metric is different. The metric is, it's all about delivering efficient RF power with low noise contribution at the lowest cost. So you want to have the most efficient power at extremely low noise, right? So your receiver noise figure should be extremely low. Your transmit power should have a high power added efficiency. And you should be able to get all of that at the lowest cost. So those are some of the things that we look at when we choose a technology. And what's key is there are different metrics for digital and RF. And this is what, like we discussed earlier. Okay, so far we have covered the 5G millimeter wave applications. So I talked about 5G fixed wireless, how phased arrays are used in fixed wireless. I talked about satellite communication, both LEO satellite communication and geo satellite communication. Again, phased arrays are used to track the beam to the satellite. I talked about wireless infrastructure, small cells, micro cells, pico cells, and again, the transition from 4G to 5G, and you're going from this huge macro base station to with one huge wide beam to these phased array antenna elements, which have very narrow beam, which gives you spatial multiplexing. So then I talked about the benefits of phased arrays, and then front-end modules. Talked about the different types of beamforming architectures. So we talked about analog beamforming. We talked about digital beamforming. We talked about hybrid beamforming. Then I talked about the impact of semiconductor technology. So the key message out there is it's your receiver noise figure and the transmit output of your power amplifier, which has a huge impact in terms of number of elements of the phased arrays. So those two parameters determine how many number of elements of the phased arrays you need to meet your system requirements. So the choice of technology becomes very critical. So now I'm going to focus on technology, and as you can see, there are a lot of different technologies that for millimeter wave interfaces. So you have RF CMOS, which can be 65 nanometer to 22 nanometer, high volume logic process technology with multiple foundries. You have 45 nanometer RF SOI. This is the technology that I'm going to focus on in this webinar. And I'm going to go in detail on this particular technology. You have 22 FTX, 12 FTX, and you have silicon germanium. All of these technologies have their own strengths, but for the purpose of this webinar, we're going to focus on 45 RF SOI technology. Why 45 RF SOI? So this is the SOI technology where the FET is electrically isolated from the substrate. So it's floating versus CMOS where the substrate is common mode. So the biggest benefit you get out of this SOI technology is you get the benefit of stacking, which enables you to have higher breakdown voltages. So your breakdown voltage of one FET is PVDS. You can stack n FETs, so you get n times the breakdown voltage of a single FET. So what this enables you to do in terms of our phased array systems that we've been talking is you can have higher power and voltage handling of the components of the phased arrays. So it provides significant benefits to front-end circuits, PAs, LNA switch. So as an example, because of stacking, you can have a higher output power amplifier. And we have shown an output of 23 dBm for the power amplifier using this technology, 45 RF SOI, with a very high power added efficiency, 43%. So again, you're getting power, again, going back to the figure of merit, right? So you want the most efficient power in RF, and that's what you're getting, a very high power added efficiency of 43% at a very high output power, 23 dBm, using 45 RF SOI in our demonstrator circuits that we have. So that was on the transmit side, so you're getting the benefits. On the receive side, you get the benefit of the back end of line. So lower losses, as you can see on the slide, because of the improved high resistivity trap-rich substrate and improved back end of line stack, we have a large distance to the substrate, which reduces parasitics and coupling. And you get, in this case, as you see on this graph, a 0.7 dB reduction in insertion loss for transmission lines while using a high resistivity trap-rich substrate compared to a low resistivity substrate. So that's kind of one of the key benefits of 45 RF SOI technology, is the high resistivity trap-rich substrate with improved back end of line losses to substrate due to parasitics. It also reduces harmonics, again due to trap-rich substrate, and improved Q in matching networks. What you will also see is we offer raised thick copper levels, and that gets you high Q inductance transformers, again helps in matching networks, low loss transmission lines, high Q MEMS, and high density MEMS. Now, as you see on the slide, there are dual thick copper levels, and they provide designers with flexibility as well. So that is some of the benefits of the back end of line, which enables you to get the low noise figure for the low noise amplifier. So to combine the two, right, on the transmit side, you had high power amplifier output power. So we have demonstrated 23 dBm, and you got that at a very high power added efficiency of 43%. And on the receive side, you had low noise figure. So we have demonstrated 1.9 dB as a noise figure, and we have some more. We are going to demonstrate some more results in RFIC, which is coming up in May, with even lower noise figures per element for the low noise amplifier. So this boils down to fewer chips per array, smaller array, so lower cost. So that's kind of like the key benefit that 45 RF-SOI provides, is in that key figure of merits that we talked about in the impact of semiconductor technology slide, and this has a huge impact on that. So to summarize, 45 RF-SOI technology for millimeter wave, because of stacking, you get high voltage and power handling. You get very good power added efficiency for the power amplifiers. Because of the low substrate loss, improved back end of line, and thick copper aluminum back of high Q, what you're getting is a low noise amplifier with extremely low noise figure. We have shown 1.9 dB, and even lower are going to be demonstrated in RFIC. In addition, millimeter wave frequencies, as you know, are 28 gigahertz, 37, 39, and then going up to 60. So we saw applications up to 100 gigahertz. So typically, you want the FT Fmax to be at least 3 to 5 times your application frequency. So 45 RF-SOI, we have demonstrated greater than 350 megahertz as the FT for this technology, 350 gigahertz. So it's an ideal technology for beamforming front-end modules, switches, low noise amplifiers, and power amplifiers. Now let's look at some of these results. This is the summary of the results, and these are all silicon-based results. We have, for the single-ended power amplifier, we are with a PSAT of 16 dBm, we are able to get power added efficiency of 41.5% at PSAT, and we have passed the ruggedness testing with 15 dBm and VSWR of 4 to 1. For the differential Doty power amplifier, we have been able to achieve 23 dBm PSAT at a PAE of 43%. For the low noise amplifier, we've been able to achieve 1.9 dB noise figure, and we have some more work which we will demonstrate at RFIC, which will show even lower noise figure than what's shown on the slide. For the switch, we have achieved our on-C of 90 femtoseconds and insertion loss of 0.65 dB at 26 dB isolation with a OIP3 of 46 dBm. These are all the 20 at millimeter wave frequencies, 28 gigahertz LNA PA switch silicon results. And these are just demonstrators that we have been able to achieve so far. And we keep on trying to get even better results, and our customers are getting better, are working with it to get newer results as we speak. So we talked about, this is an example of, again, PAE, output power. So as you change the output power, what's the impact of PAE? So that's like at 16.2 dBm, the PAE is 41.5. At P1 dB, you have a 14.2 dBm P1 dB with a PAE of 37.3%. And this was, we were able to achieve this because of FET stacking, which enabled us to achieve high PSAT and high PAE results from the low loss and matching network. This is the result for the low noise amplifier. We have seen great model to hardware correlation, full on-chip matched LNA, cascode one stage, and a gain of 11 dB with a noise figure of 1.9 dB. And again, this is with the high resistivity substrate with optimized back end of line, which helps reduce parasitics and improve LNA noise figure. And then this is for the switch. We have achieved insertion loss of 0.65 dB with our IP3 of 46 dBm, R1C of 90 femtoseconds. And this is, again, we passed reliability at 20 dBm ruggedness testing as well. And now I want to show you some system-level applications of the different technologies. So this is your front-end module with digital beamforming. So you have the phased array antenna elements, you have this front end, and then you have RF up-down converter ADC DACs, and then you have the baseband. So you can use different technologies. So 45 RF SOI you can use only for the front end up to the LNAPA, or you can have the IF up and down converter as well and get it down to the baseband. 22 FTX you can get, have front end IF up down conversion as well as ADC DACs and even integrate the baseband, or you can have FinFET technology for the baseband. So there are multiple technology options based on which you can choose the architecture and chip partitioning. This is for infrastructure. The earlier slide was an example for a UE device, so a handset. This is for the infrastructure. I've shown hybrid beamforming. So with hybrid beamforming, you have both analog beamforming at the front end and then digital beamforming at the digital domain. So you can again use the different technologies shown. You can use 45 RF SOI, or you can use silicon germanium PA LNA with a 45 RF SOI switch. You can use 22 FTX transceiver, and then for the baseband you can use 14/7 nanometer FinFET or 12 FTX technology. So again, the choice will depend on your system requirements, your array size, your effective isotopic radiated power, your chip partitioning technology selection. So those are some of the key parameters. But the key thing again to note is, again, the two things which are most important is what is your transmit output of your PA in the technology that you choose and at what power added efficiency, and then what's the noise figure of your LNA. So those are two things that will determine the number of elements that are needed in your phased array systems to meet the requirements. Okay, so to summarize, let's say from a summary perspective, what's key for all of this, right? So the essential elements for millimeter wave system design are you need a technology with high performance. So high FTF max should be at least 3 to 5 times of your application frequency. You need higher performance to enable design techniques for more robust design. You need low loss back end of line, right? So thick top metals, distance to substrate, substrate resistivity. You need well-modeled technology. So RF model to hardware correlation is key to minimizing design iterations. You need good parasitic extraction deck and electromagnetic simulation tools. So scalable transmission line, millimeter wave passive process design kits, library minimized time spent custom EM simulations. So an accurate process design kit, in addition to high performance millimeter wave technology, is key to meeting specs without too many iterations. So millimeter wave, so I'd like to summarize this presentation today. So millimeter wave phased array systems help reduce transmit power per element. We talked about that. Unique features of SOI technology like FET stacking, transistor stacking, reduced junction parasitics, low loss interconnect, and high FTF max help build an efficient millimeter wave phased array system. And then different architecture and chip partitioning options exist depending on application specifics and constraints, which can be addressed by using global foundry technologies. Okay, thank you so much for attending the webinar today, and now I'm going to open it up for questions.
Well, Jeet, thank you for a very informative presentation and sharing your knowledge. You certainly covered a lot of material. We do have some time for questions, so we'll invite our audience to pitch in. If you have a question, you can type it into the Q&A box on your screen, and we'll see how many questions we can cover in the next few minutes. And of course, Baljeet will get a copy of all the questions, even if we don't have time to answer them. So our first question is, can you give us a sense of the technology adoption in the market for the 45 RF SOI process?
Great question. Thank you, Gary. So from a technology adoption perspective, we have several customers right now designing with this technology. So we run Moses MPW, which is run every quarterly. So we ran that in all of 2017, and we had several customers on each of these Moses MPW runs. So this technology is in full production. So we just did a press release introducing this technology to the world in terms of we have customers who are designing with it. We'll have the first prototype of a customer getting into production in 2018, so second half. So it's really ramping up. So we've seen the key benefits that this technology offers are, right, you have the FET stacking. So because of that, you are able to get high power amplifier at output at a very high power added efficiency. And then again, for the receiver, you are able to get extremely low noise figure. So the combination of those two enable you to get extremely less number of phased array elements for the same system performance. That's what our customers are also seeing. And because of that, we've seen very rapid adoption of this technology in the marketplace. So yeah, and I think a lot more to go ahead.
So one of our viewers has a question about the higher frequency applications. Can you use RF SOI for 60 gigahertz and above?
Absolutely. So like I was mentioning in the presentation, right? So you have, you want your FT Fmax to be at least 3 to 5 times your application frequency. So in this example, 60 gigahertz, that's actually a very commonly used WiGig frequency as well. And we have customers designing for WiGig today with 45 RF SOI. So 60 gigahertz, I mean, 3 to 5 times of that is 180 to 300 gigahertz. And the FT Fmax for this technology is greater than 350 gigahertz. So effectively, this is an ideal technology for millimeter wave applications up to 100 gigahertz.
Okay. Can you talk a little bit more about a system topic in the sense of what are the key figures of merit that will determine the number of elements in the phased array?
So I think the critical thing about phased arrays is they enable you to have a spatial multiplexing. And the way they do that is you have phased arrays with very focused beams. Now, the number of elements of the phased array is critical. And also what's critical, because that will determine how big your phased array is. And then based on how big your phased array is, you will determine your beamforming scheme, whether you will have analog beamforming, or you'll have digital beamforming, or you'll have a hybrid beamforming. So all of these approaches are all interrelated to how big your phased array should be. And that is dependent on two factors, actually a multitude of factors, but the most important ones, in my opinion, are the noise figure and your transmit output power for each element. So if you can have a very high transmit output power for each element of the phased array, and then same thing on the transmit side, and on the receive side, if you can have extremely low noise figure for a phased array, low noise amplifier, then you can have the least number of elements in a phased array. And what that boils down to is your most cost-effective phased array system. And that's why it's critical to have a technology which can give you the very high output power at a very high efficiency, power added efficiency, as well as a low noise figure for the low noise amplifier, which is extremely low. Those are some of the key benefits.
Okay. Follow up to that question. Go ahead.
And that's how you get the number of elements in a phased array. Thank you.
Okay. So a follow-up question in terms of the some of the results that you discussed. Have they been published? And specifically, the viewer is asking, for example, the noise figure that you cited of 1.9 dB.
Yes, all of this are published in various papers that we have presented at RFIC, at IMS, and that's the reason why I also said we have results which are better than 1.9 dB, and they will be published at RFIC in May, and so that's why I did not go over that in this presentation. But we can, of course, share. If the viewer is interested, he can send me an email, and I will be happy to share the link of the different papers and also go through the designs with them.
Okay, process-oriented question here. Can you talk about back biasing in fully depleted SOI? Does it help in operating fully depleted SOI in high frequencies, at the high frequencies?
Yes, so I think, so from our perspective, 45 RF SOI is PDSOI, partially depleted SOI, and we do not have back bias. So we have huge substrate isolation, so it's fully isolated, and no backside contact. So what you're mentioning is only found in FTSOI.
All right, so let's squeeze in one or two more questions since we're at the top of the hour. How would you compare the efficiency and noise figure of SOI versus SiGe 130 nanometer and 55 nanometer?
So what's critical out there is what we have been able to achieve with this 45 RF SOI, right? So for 45 RF SOI, we have been able to achieve an output power of 23 dBm at a very high power added efficiency of 43%. Of course, it depends on the output power level for the power amplifier in terms of silicon germanium. So if you compare with SiGe, you can even get higher output power, but it comes at a cost and the efficiency, right? So those are some of the trade-offs that you have to consider between your choice of how much output power you need at what efficiency. SiGe can probably go to slightly higher output power, but 45 RF SOI has superior switch versus the silicon germanium technology. And then the whole package of combining your power amplifier, your switch, and your low noise amplifier is exceptional. I mean, that's kind of what you get is that integration. And we have an exceptional low noise amplifier in 45 RF SOI. So again, I mean, different technologies have different trade-offs, but what we have seen is the sweet spot of combining the switch, the LNA, and the PA with 45 RF SOI with an exceptional switch. We have been able to get RONC of 90 femtoseconds and isolation of over 25 dBm at millimeter wave frequencies, and again, output power of 23 dBm at 43% PIE, as well as LNA with 1.9 dB noise figure, which we are showcasing a better one in the RFIC conference that's coming up in May. So those are some of the trade-offs.
Right. Last question. Does the quoted 45 nanometer SOI PA efficiency that you cited include the losses of the on-chip matching network?
Yes, it includes the losses in the on-chip matching network. So this was like, yeah, that's correct.
All right. Well, unfortunately, we've run out of time for more questions, but as I mentioned earlier, all the questions that did not get answered will be given to Baljit so that he can possibly follow up, or you can also contact Global Foundries if you have very specific interests. So I would like to thank Baljeet Chantok and Global Foundries for today's webinar, very informative on design innovations in 5G millimeter wave front-end modules and phased arrays. The next few years should be quite interesting as this technology gets deployed. This webinar has been recorded and will be available to watch within about an hour. You'll find it at the event section of the Microwave Journal website. And if your colleagues would benefit from watching it and weren't able to attend the live event today, please let them know so they can watch it on demand. Thanks everyone for joining us today.